Yogah Karmasu Kaushalam.
Good morning, everyone. I heartily welcome you all in the online refresher course in chemistry hosted by Department of Chemistry, School of Sciences, Gujarat University, Ahmedabad, on behalf of Dr. Jagdish Joshi, Professor, Director, UGC HRDC, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, Department of Chemistry, School of Sciences, Gujarat University.
In the next session, we would encounter Dr. Rajesh Kamble, Professor, Department of Chemistry, University of Mumbai. He is having 20 years of experience in teaching and research. His thrust area of research interest include designing, synthesis, and characterization of novel AIE functional organic materials for application in OLEDs, solar cells as chemosensor and for bioimaging purpose. He has done supervision of 84 MSc projects, has guided 2 PhD students, and currently have 6 PhD candidates under his guidance. He has fruitfully completed 3 research projects funded by UGC, DST SERB, India. He has total 33 publications with 6 national and 27 international. Moreover, he is reviewer for journals like RSC Advances, Chemistry Select, New Journal of Chemistry, Journal of Material Chemistry, Journal of Molecular Structure, Journal of Chemical Sciences, and many more. He has also presented 40 papers and conferences at national and international level. He has delivered 11 lectures at various universities, research institutes, in conferences. Additionally, he was secretary of UGC SEP-sponsored National Conference on Research Development in Chemical Sciences 2018. He has also served as coordinator of refresher courses and worked as coordinator of IQAC in various committees at university level.
Myself, Dr. Rajesh M. Kamble. I'm professor in Department of Chemistry, University of Mumbai. Let me first of all thank the UGC HRDC Center of Gujarat University for giving me this opportunity to connect with you and deliver my session on the topic DAD-based pyridopyrazino 2,3-B indolamines, photophysical, aggregation-induced emission, and electrochemical studies. I thank Dr. Jagdish Joshi, Professor and Director of UGC HRDC, and Dr. Dilip Vasawa, Course Coordinator, Department of Chemistry, Gujarat University. The HRDC of Gujarat University is ranked as 15 in India and number 1 in Gujarat state. It is pioneer and created history, a benchmark, by organizing various courses by online mode as well as offline mode. And I congratulated the UGC HRDC and the coordinator and the director for this achievement. So with this, let me tell you about the outline of my talk. These are the points which I will cover within next hour. The importance of donor-acceptor architecture, which is required in organic semiconductor. Benefits of organic or inorganic molecules as semiconductor. I'll go through a little bit history of these organic semiconductors, classification, applications of these organic semiconductors, current challenges and optoelectrochemical properties of organic semiconductors, about the phenomena like aggregation-induced emission and thermally activated delayed fluorescence and its importance. And at last, the pyridopyrazine indole, which is used as an acceptor in donor-acceptor assembly, which the molecules we have synthesized and studied for their optoelectronic properties. What is this DA architecture and how it can be helpful in organic electronics? You can see over here, donor acceptor architecture is a well-known strategy which is utilized for development of molecules which are beneficial for their applications in organic electronics. In optoelectronic devices, this DA architecture is used for main four purposes. First one, to develop blue, green, yellow, and red emitters, which are applicable in the display technology like organic light emitting diodes as well as the lighting technology. Second, to obtain the hole and electron charge transporter. Third one, to absorb the broad spectrum of solar radiation in dye-sensitized solar cells. And the fourth one is the electron or N hole or P transporting and ambipolar charge transporting materials, which are useful in organic field effect transistors. This DA approach helps to effectively engineer the optoelectronic properties of conjugated molecules, such as to get the broad emission from blue to red, a good band gap, a decrease in band gap, etc. via intramolecular charge transfer, that is ICT. The role of DA architecture you can see in organic semiconducting die. So it has this various, I can see the importance. The DA architecture in a molecule facilitates intramolecular charge transfer, decrease in band gap, facility to structure modification. We can easily modify the structure of this molecule by altering or changing either the donor segment or the acceptor. Thus, we can add these two segments by changing these two segments as the donor or acceptor, and thus extend the conjugation in that molecule, which is responsible for active charge transfer, that is either the hole or the electron. The DA architecture allows to tune photophysical and electrochemical properties, also helps to induce the aggregation-induced emission property in a molecule to obtain the solid-state emissive materials, which are highly required in real-time applications, the display technology applications and the lighting technology applications. And this DA architecture also helps to induce the thermal stability in these molecules. Now, what are the benefits of organic or inorganic semiconducting DA materials? Now, let's just see some basic, again, see the fundamentals about organic semiconductors. Organic semiconductors, these are compounds whose building blocks are pi-conjugated molecules or the polymers, which are made up of carbon and hydrogen, basic elements, and sometimes also have the heteroatoms like nitrogen, sulfur, or oxygen. Organic semiconductor is an organic compound which possesses similar properties to inorganic semiconductors with holes, electron conduction layer, and a proper band gap. Now, this figure you can see over here. So, this tells us about the metal, the semiconductor, and the insulators. So metals, there is a very negligible against the band gap. So metals are good conductor of heat and electricity. Insulators, the band gap between the valence and the conduction band is high. So that's why such kind of materials cannot conduct the heat and electricity. And semiconductors lies in between these two, metal and insulators, so which has this band gap up to 4 electron volt. Now let's see about the benefits of organic or inorganic semiconducting DA materials. Now, advantages of organic semiconductors, they have the low molecular weight, simple structure, We can synthesize this molecule, prepare this molecule very easily, means the synthetic routes are easy. Purification of these kind of molecules is very easy. You can see this in its pure form. Reproducibility is there. Ease of structure modification to tune the optoelectrochemical properties by changing either the donor or acceptor segment. And solution processability there with better solubility of these molecules in various organic solvents. And we can have these molecules, applications of these molecules in display technology, that is flexible displays. You can see the images over here. This is the era of organic semiconductors. Now let's go through the journey of these organic semiconductors. First of all, Martin Pope, they found the electroluminescence in organic compound, which was reported by them in 1963 by passing a very large voltage through anthracene crystal. Later on, in 1973, this trio, Alan G. McDiarmid, Shirakawa, and Higa, reported high conductivity in oxidized and iodine-doped polyacetylene. And for this invention, this trio, they were awarded Nobel Prize in Chemistry in 2000. Then, in 1987, Tang and Van Slyke, where those who were working in the Kodak laboratory, they fabricated the first organic electroluminescent device in Kodak laboratory. And this is the seminal work that first time in 1987, see the first OLED device came into existence. And the world's first OLED television was introduced by Sony in 2007. Let's see about the classification of these organic semiconductors. Organic semiconductors are broadly classified on the basis of their molecular weight and the electronic properties. On the basis of molecular weight, as a small molecules are also called as oligomers, and the large sized molecules are the polymers. But these are the examples of small molecules like perfluoropentacin, tipspin, and the polymer like polythiophene, polyphenylbromine. Molecular weight below 1000 are called small molecules, and polymers having the molecular weight above 1000. On the basis of electronic properties, organic semiconductors, these are subclassified as p-type or hole transporting materials, n-type or electron transporting materials, and ambipolar charge transporting, which transport both the charges in the molecule. Now, applications of these organic semiconductors. Organic semiconductors have these wide applications. These are having applications in organic light emitting dyes. This is the display technology. Nowadays, we use the screen, we find the screens of mobile phones, the desktops, the televisions, which use these organic semiconductors. In lighting technology, also they have the applications. In RFIDs, organic lasers, organic photovoltaics, like solar cells, and organic field effect transistors, and as well as in case of the sensors. So these are the applications of organic semiconductors. Now, what are the current challenges and beneficial electrochemical properties of DA-based organic semiconductors for their applications in organic electronics? Now, three terms are very important here, or the phenomena that I am going to discuss in case of the pyridopyrazine molecules. And that is aggregation-induced emission, ambipolar charge transporting properties, and the thermal activated fluorescence, that is TADF. Now let's see about this AIE property. to obtain the aggregation-induced emission, that is AI activity in molecule for their solid-state application in organic electronics. So what is this AI? AI is interesting photophysical phenomena in which the molecules are non-luminescent in their dilute solutions, but become highly emissive in their aggregate or solid state. And for this, the RIR effect, it helps. Restricted intramolecular rotation. And this AI overcome aggregation concentration quenching, that is ACQ, effect, that is detrimental effect, as explained by Tang and his colleague in 2001. So what are the conditions required for a molecule to be AIE active? So the molecule should be non-planar in conformation, propeller in shape, and there must be restriction to the intramolecular rotation or vibration or rotation plus vibrational motion in solid state. Let's see one of the example. Okay, the example of this AI active molecule. So this is hexaphenylsilol. Centrally placed, this HPS is having centrally placed silol, which acts as a stator, which can't move. Attached to it, the 6 rotatable phenyl rings. Now, this HPS hexaphenylsilol in its solution state, it is non-emissive. There is no emission because all these 6 phenyl groups, they rotate and acquire a planar geometry in the solution state because molecule in the solutions are in free state. But when it comes in the aggregated state, a solid state, then we can find out this a restriction of intramolecular rotation. Now this HPS molecule acquires the propeller shape. There is restriction on the rotation of these phenyl rings around the silol stator. These are the rotors which rotate 6 phenyl rings. And this acts as the silol centrally placed acts as a stator which can't rotate. So in solid state, aggregation state, there is limitations on the rotation of the 6 phenyl rings around this stator silol, and it acquires the non-planar geometry. And thus, it becomes emissive in solid state, highly emissive in the solid state because of its non-planar geometry, propeller shape, and there is restriction of intramolecular rotation. Now, what is the principle behind this AI activity? Now, planar geometry trained to aggregate as a disk piling due to the strong pi-pi stacking interactions between the aromatic rings, which commonly turns off the light emission. Now we'll see the example of beryllium is contains aromatic cysteine. So this is emissive in its solution state, having 6 pi conjugation. But in its solid state, it shows the aggregation caused quenching. It becomes non-emissive. Emission goes off because of this pi-pi stacking interaction. It's a pi law. Molecules, they arrange one above the other and thus form a disk of pi, and that is called the pi-pi stacking interaction. So the molecule, this beryllium, which is emissive in its solution state, shows the aggregation caused quenching in its solid state because of this pi-pi stacking interaction. Whereas non-planar or twisted luminophore, due to restriction of the intramolecular rotation, that is called as RIR, of the multiple phenyl rotors. In case of this hexaphenylsilol, multiple phenyl rotors, this acts as a donor against the stator, that is acceptor. Silol is acceptor, and this 6 phenyl rings acts as a rotors. In the aggregate state, the light emission turned on by aggregate formation and hence have this AI activity. Now hexaphenylsilol, just I described in the previous slide, is non-emissive in solution state. But in aggregation state, in solid state, it forms with the propeller shape. And there is restriction of the intramolecular rotation. All 6 phenyl rings avoid the rotation around this stator silo and thus forms with this non-planar shape. And there we can find aggregation induced emission. It becomes emissive in its solid state. Other examples we can see, famous against is a dye, it's a green fluorescent dye, fluorescent. It is highly emissive in its solution state. But in its solid state, the emission goes off. Because of this xanthine thing, you can see the pi-pi stacking and traction is there. And then we can see this aggregation cause quenching, ACQ. But another molecule, AI active molecule, is the TP, that is tetraphenylethylene. Tetraphenylethylene. So in its solution state, it is non-emissive, but in its solid state, it becomes emissive because again, this TP is having the 4 rotatable phenyl ring and central is what ethylene or ethene. And this acts as the stator and these 4 phenyls as a rotor. So that's why in solution state like this HPS, hexaphenyl silo, it is non-emissive, but this ACQ again see this emission is, you can see this good emission when it comes in solid state because of this RIR, restricted intramolecular rotation. Okay, and we get this aggregation induced emission here, AI property. So these are some examples of how in case of some molecules, they are emissive in solution state, but because of pi-pi interaction, pi-pi stacking, so non-emissive, emission goes off in solid state. And these molecules, which are having say, this propeller shape or the non-planar conformation or geometry, so becomes emissive in their solid state and non-emissive in their solution state. Now, how to meet the requirement of ambipolar or electron transporting materials for organic electronics? If you go through the literature, we can find out the number of against these organic semiconductors are reported as a p-type hole transporting materials, but electron transporting and ambipolar charge transporting materials are lacking behind. Outstanding development in the hole transporting materials witnessed higher mobility than amorphous silicon. And the development of electron transporting materials, that is N-type and ambipolar materials, is still lagging far behind as compared to the hole transporting materials because difficult in their synthesis and this N-type or ambipolar molecules are unstable in presence of oxygen and moisture. So ambipolar property prevails when molecules have HOMO level greater than or equal to 5.6 electron volt and low-lying LUMO level approximately 3.15 electron volt, or LUMO it should be between 3 to 4 electron volt. And ambipolar materials enhances the power efficiency of the devices because it acts in both hole and electron transport and hence requires or it's a need of the development of it. Now about the TADF, that is how to obtain the metal-free thermally activated delayed fluorescent materials, TADF materials. Now major of the research is what worldwide going on to develop thermally activated delayed fluorescent materials, organic materials. TADF materials are beneficial in the field of organic light emitting display technology, owing to their efficient triplet exciton harvesting via reverse intersystem processing, RISC process, from the lowest triplet T1 to the lowest singlet excited state X1. Because if you find, see, when we excite a molecule, the molecule electrons, they get excited from ground state S0 to S1 level, that is singlet excited state. And to only 25% of the excitron, they return to the ground state with characteristic emission of light. And 75% of that excitron goes to the triplet state, T1 state. And thus, the internal quantum efficiency is only 25%. Now, how to recall that 75% of that excitron? So that I can see is possible by development of this TADF materials. Now, TADF materials is of low cost, carries lower pollution in view of practical application, and can achieve maximum internal electroluminescence efficiency. That is just I told you of approximately 100%. So this is nothing but just harvesting of that 75% of excitrons which goes in the triplet state. We used to harvest that 75% with this 25% of the excitrons which are there in this singlet excited state. And thus we get this 100% of this internal quantum efficiency. So which is comparable with that of phosphorescent OLEDs. Now, most of TADF materials are metal-based, organic electroluminescence molecules, that is organometal. While pure organic TADF emitters represent a promising pathway towards high performance, low cost, full color, and white OLEDs are still behind. Now, potential TADF molecules need a minimized singlet S1 to triplet T1 energy gap. That is called as a delta EST, is to denote by delta EST. That is singlet triplet energy gap minimum, which leads to an easier RISC, that is the reverse intersystem crossing at a given temperature. If there is minimum singlet to triplet energy gap, we can recall back that 75% of that excitron goes in triplet to the singlet one, and thus acquire the 100% internal quantum efficiency. And that is possible only when the energy gap between the singlet and triplet is very minimal. And the theoretical approach for obtaining a small delta ST can be achieved by separating the wave function distributions of the HOMO and the LUMOS. Now, based on this simple electron configuration recipe, a number of TADF emitters with small or even vanishing delta ST gap have been reported in the literature, which contain highly twisted molecules composed of TA moieties. To get the TADF materials, the geometry of the molecule, it should be when in their solid state or aggregated state, it should be, the geometry should be non-planar. Highly twisted, okay, structured molecules can show the TADF properties. Now, why pyridopyrazine 2,3-B indole here? Now, what are the molecules I am going to discuss here, the properties of these molecules that contains this pyridopyrazine indole as an acceptor. This pyridopyrazine indole is a mimic conformer of indole 2,3-B quinoxalate, which possesses additional pyridine nitrogen atoms in the fused ring of the molecular framework. Now, these are the structures of these molecules. I'm going to discuss the photophysical, electrochemical, and theoretical properties of this molecule. Now, this centrally, the blue structure you can see is a pyridopyrazine indole. Attached with this are the donors, amine donors, different amine donors. Now, pyridopyrazine indole is a mimic structure of indole quinoxalate. If we have a carbon atom over here in this, so it becomes indole quinoxalate. And having nitrogen here, okay, it becomes the indole pyridopyrazine. The past reports on this code are only based on its synthesis and some biological activity. And while its optoelectronic properties are recently reported first time by our group. The use or utility of pyridopyrazine as an electron acceptor core in optical devices are as a result of its diverse active reaction sites, simple molecular structure, simple preparation of its derivative by condensation between 2,3-diamino pyridines. I'll discuss the synthesis of these molecules in next slides. And benzyl derivatives, suitable electron withdrawing ability for systematic or fine tuning of the optical band gaps, and some other optical properties, modulation in donor, and having multiple sp2 hybridized nitrogen centers, which also favor the intersystem crossing, that is IS. Moreover, introduction of fused aromatic indole donor. You can see this is the indole, which acts as a donor within this molecule. Indole donor rings into the pyridopyrazine electron acceptor core lead to. Now this is your indole pyrazine. Sorry, this is pyridopyrazine and this is your indole. So fusion of this lead to establishing intramolecular, that is push-pull system, and ICT, intramolecular charge transfer characteristics in it for optoelectronic applications. Second, it can modify electron accepting strength, change in band gap, and the fluorescence efficiency with enhanced solventofluorochromism and AIE properties compared to pyridopyrazine acceptor-based TA system by optimizing the intramolecular charge transfer strength. And third, mixing of multiple embedded mixing of multiple embedded or added nitrogen atom in pyridopyrazine indole with an intrinsic and by transitions nature and charge transfer excited state form in fused polyheteroaromatic product, that is pyridopyrazine indole, that serve the efficient charge separation in HOMO-LUMO orbital, resulting in reduction of delta EST, that is energy gap between singlet and triplet, and potent TADF emission efficiency. Therefore, this pyridopyrazine 2,3 indole derivatives could be advantageous for serving multifunctional role in optoelectronics. Now, these are the molecular structures of this donor acceptor donor dyes, which we have synthesized in our lab and studied for their optoelectronic properties, for their possible applications in organic electronics. Now, centrally placed is your the pyridopyrazine indole, which acts as an acceptor, and at both this side, third and seventh position, added the donor or attached donor moieties. This is, in this case, is a diphenylamine donor. In this case, is a naphthylphenylamine donor. Here is the having methoxy, that is donor group, substituent group on this phenyl, and the two heterocycles donor heterocyclic amines, the carbazole and the phenothiazine. So thus we can form the donor acceptor donor kind of molecules here, or these dyes, which are emissive as well as which can serve as an ambipolar charge transfer materials on the basis of their characterization. Now this is the reaction scheme. This is pyridopyrazine indole, dichromopyridopyrazine indole is prepared by condensing this indole dichrome and this diamine, pyridine diamine, and we got this the adduct, and then by using the Buchwald-Hartwig amination reaction using these different amines, these are given number 2, 3, 4, 5, 6. Okay, diphenylamine, naphthylamine, methoxy substituted diphenylamine, this cyclic carbazole and this phenothiazine, and by using Buchwald-Hartwig amination reaction, so it is called 5 molecules are obtained. Now let's see about this visible absorption property or photophysical properties of this molecule, absorption and emission properties. This is the absorption spectra of 1 to 6. 1 is what your adduct, the central moiety, and 2 to 6 are these amides. The absorption peaks below 400 nanometer. The intense transitions you can see here. Below 400 nanometer belongs to the N to pi star and pi to pi star transitions of within this entire molecule. And the less intense, weak transitions above 400 nanometer witnessed as a result of the intramolecular charge transfer transition, which is established in cases of these molecules as an DAD architecture, that is donor, acceptor, and donor. Charge transfer takes place from donor to this acceptor. And this table, the red values you can see, these are the lambda max of the wavelengths for charge transfer transitions, ICT, intramolecular charge transfer transition. In case of solid film also, you can see the N to pi star, pi to pi star transitions below 400 and above 400, that is the rate shifting in solid state absorption as compared to their solution state. The absorption spectra suggests a molecular implication. So thus, these type of transitions are called as the ICT transitions, or these are confirmed as the ICT transitions. And the absorption of these molecules or the transitions in case of these molecules, again, you can see the little bit change in that based on the donating property of these amines within these molecules. The molecule fourth and third, molecule fourth, which is having this methoxy, again donor substituent of this diethylamine, and the third is having extra phenyl ring over here, so shows the bathochromic shift as compared to the other molecules due to extension in conjugation, pi conjugation in these molecules. Now about the fluorescence properties, the molecules emits blue-yellow color or emission in the range of 433 to 563 nanometer in their solution state. Now we have used the THF, tetrahydrofuran, chloroform, DCM, and DMSO, and toluene. These 5 solvents were taken to these emission spectra of this molecule. The absence of vibronic structure in emission spectra of 2 and 5. 2 is where we have diphenylamine as donor, and 5th is a carbazole. Suggests that the long wavelength emission is due to a relaxed intramolecular charge transfer state. You can see this emission wavelength in toluene, DMSO, and stock shift, these are mentioned in the toluene, and band gap is given here in DCM. While in case of di 3, 4, and 6, in case of di 3, 4, and 6, having naphthylphenylamine, methoxy, substituent on diphenyl, and carbazole. Sorry, this 6th one is the phenothiazine, shows the dual or multiple emissions here, which could be due to the emission from the relaxed locally excited states, which occur near 433 nanometer, as well as from intramolecular charge transfer state emitting at longer wavelengths in between this wavelength 458 to 563. A variation in emission from relaxed intramolecular charge transfer state with modulation in donor segment and increasing electronic conjugation follow this trend, as 4th one is having methoxy substitute. So shows this emission at 460 nanometer. Then 3rd, which is having this naphthyl extra phenyl ring, 459. Then 6th is having phenothiazine donor. 5th is having carbazole, and 2nd is diphenylamine. In case of 3 and 4, you can see the bathochromic shift in the emission wavelength because of this methoxy, extra methoxy donor substitute group and this extra phenyl ring in this donor party. Now, these are the emission images of 2 to 6, which are in toluene, THF, chloroform, DCM, and DMSO. The emission maximum of dyes 2 to 6 were found slightly sensitive toward the solvent. As we change the solvent, polarity of the solvent, either we can see the bathochromic shift in that or the rate shift in that, that is termed as a positive solenochromic effect. And that also found in case of these molecules as we move from less polar toluene to highly polar DMSO solvent. The dyes 2, 5, and 6 shows high Stokes shift, suggests a change in the ground and excited state geometry, and there is no reabsorption of the emitted photons, measuring its desirability in optoelectronics. The molecules which can be used in the optoelectronic application should have either good Stokes shifts or high Stokes shifts. Now, besides, dye 3 and 4 emit at a shorter wavelength compared to ICT. See the table, it's dye 3 and 4. 3 and 4. And third is having this naphthyl phenyl, and fourth is having the methoxy group. This emit at a shorter wavelength compared to the ICT absorption maximum and show the anti-Stokes shift characteristics. That you can see the Stokes shift of this molecule, third and fourth, goes in negative. Anti-Stokes shift. So, this could be due to the existence of hot band absorption process, or it's also called as the triplet annihilation, TT, based up conversion process. And such anti-Stokes shift based luminescent materials are utilized for bioapplications. Further, the optical band gap of dyes are found in the range of 2.19 to 2.85. These are the optical band gap. The adduct is having 2.64, and other molecules we are able to reduce the band gap up to 2.21 by changing or addition of the donor groups on that central accepting moiety, pyridopyrazine, indoor moiety. And the fluorescence quantum yield of this 2 to 6 in variety of these solvents are in the range of 1.85 to 15.18, which are calculated using quinine sulfate as a standard. The solenochromism in case of these molecules was studied by various polarity index parameters. In this figure, you can see the plot of emission wavelength. I see the Richard empirical solvent polarity parameter ET30, Richard Demont function. Both this A and B, Richard polarity parameter ET30 and this Richard Demont function, they tell us about this positive solenochromism in these molecules when we move from non-polar THF to highly polar DMSO solvent. That tells us about this excited state are more polarized than the ground state. Again, this Richard polarity parameter and Richard Demont, so which are plotted versus Stokes shift, that is in this figure E and F. This tells us about the stabilized ICT state in polar solvent. The intramolecular charge transfer state is stabilized in highly polar state. We get the good correlation against this factor number about 0.9. And polarized ICT state. So that's why we get to the broader peaks in case of ICT, intramolecular charge transfer. Then the Wheeler's function and the Rettich's functions, Wheeler's in this figure C and D, and the Rettich's functions. So they tell us about the possibility of TICT state, that is twisted intramolecular charge transfer state. And that is highly required to get the AI active and TATF molecules. So here it shows the better charge transfer or charge separation between HOMO and LUMO, twisted conformation for AI and TATF character, possible AI and TATF character. And the other, that is Lorentz Lorentz function, and Kirkwood-Magath, G and H. So these tell us about the independence of solvent polarity on refractive index of solvent and dependency of solvent dielectric polarizability. And the three figures, this I, J, and K, that is Lippert-Mataga polarity function. This one in this figure is I. So tell us about this positive solid equilibrium with confirmation of charge transfer characteristics in these tracks. And this J and K plots, these are for Macrae function and this is for Bakshi function. These are the modified version of the Lippert-Mataga. I can tell us about this confirms the positive solid equilibrium when you change the polarity of the solvents, and thus confirms the presence of charge transfer characteristics in this molecule, that is DAD kind of characteristics in these molecules. Now this is about the solution state emission properties of this molecule. About solid state emission property in these molecules, you can see this figure, emission spectra of compounds 1 to 6 in solid state, so solid film. And these are the emission images of 2 to 6, which amines in solid film and powder under 365 nanometer UV illumination. So these are the thin film solid films prepared, and these are the solid powders. Now the solid state emission of dyes 2 to 6, except 4, that is having methoxy substituent or diphenyl, that is non-emissive in solid state, covers broad range of emission from blue to red, that is 470 to 600 nanometer, and follows the trend as the molecule 2 shows emission at 470 nanometer, 5 having carbazole 471 nanometer, 6 having phenothiazine, these two wavelengths, and third is having naphthylphenol 600 nanometer. Now we got to the good solid state emission. In case of DA pairs, a DA molecule is like 2, 5, and 6. 2 is having diphenyl donor, 5th is having carbazole, cyclic amine donor, and 6th is having phenothiazine. This may exhibit aggregation-induced emission. That is AI properties which would be advantageous or useful for their application in organic electronics. It's the general concept that the molecules which show the good emission in their solid state may have the AI property. And blue shift in absorption and emission of dyes 2, 5, and 6 suggest non-planarity in it, and hence attain the propeller shaped conformation, which suppress the intermolecular pi-pi interactions, which leads to the increased emission intensity in its aggregate or solid state with AI effect. And this AI effect in case of this molecule, this is the figures and images are shown in case of this molecule second, which is having diphenylamine donor on this acceptor molecule. AI and size dependent emission. This figure is the emission plot, emission spectra, and the solution images of this second molecule. Now, AI property of these molecules are studied in mixture of two solvents. One is organic solvent, here selected is a THF, and water as a non-solvent. You can see here these vials which can show images in visible lamp and the UV lamp. So in first vial is molecule is in only THF solvent that shows the emission due to ICT transitions, intermolecular charge transition. Then we increase the percentage of non-solvent water by 10% in each vial. Like here is the 10%, 20, 30, 40, 50, 60, 70, 80, and 90. Now, increase in water percentage of water shows little bit change in emissions. The emission decreases as the water percentage water increases. Now, in this figure, you can see the plot of this emission intensity versus the water fraction. As you change the water fraction, now you can see at 10% water fraction, you can see the good emission here, and that indicates this mixture of solvent, this molecule is water sensitive, and thus it may have the applications in the bioimaging. But the emission, it goes up as you increase the water fraction, and the stage comes here at 60% of water fraction. You can see the AIE property, aggregation induced emission. Now the formation of nanoparticles in these various water fractions is confirmed by the DLS technique. Now you can see over here, figure 8. These are the DLS plot of these two molecules, second molecule, in various water fractions. Now here 60%, 70%, 80% water, and 90%. You can see the change in particle size of this molecule. That means at this higher water fraction, the polarity of this water, now the hydrophobic environment it creates, and the molecule, it starts aggregate state, but at a nano level. Generally, what happens in organic solvent like a THF, organic compounds of these molecules are in the soluble state. But when you add this water, non-solvent, you can see generally the bathochromic shift by decreasing emission intensity. By decreasing, but in case at 10% water fraction, the emission intensity what it is, that shows the sensitivity to this water, but emission goes on decreasing. But at this 60% of water fraction, where the hydrophobic environment it creates and the molecule starts solidifying, comes into its aggregate state, but at a nanoparticle. And that is confirmed by this DLS technique. You can see here the suspension of these nanoparticles at this 60–70%. At 60% of water fraction, the particle size of these molecules in their solid aggregated state is 140 nanometer. Then it changes to 70%, 187. 80% is higher, 380 nanometer, and 90% is 454. Thus, it shows the other shape of this nanoparticle. It varies from 60% to 90% as the particle size is what increased, because the change in against the water fraction is there. Thus, it affects on the molecular geometry and conformation also. So we can see the different against the particle size of this aggregated nanoparticles of this compound 2 in these different water fractions. And thus, at 60%, we can confirm this molecule comes in its aggregated state or nanoparticle state and shows the aggregation induced emission. You can see at this water fraction 60, okay, and 70, you can see the good emission here. So thus confirm here this aggregation induced emission, and the emission also, again, so you can see the change in emission. Okay, here the emission goes down as the particle size of this molecule, okay, it increases. That is about this detailed photophysical studies about absorption and the emission properties and the aggregation induced emission in case of this molecule. Now, to claim these molecules as an p-type or n-type or ambipolar charge transporting materials, we have characterized these molecules by electrochemical technique, that is cyclic voltammetry. And the cyclic voltammetry of these molecules shows both the oxidation and the reduction potentials. This is the full scan of this molecule too. and this is the half scale. You can see here the oxidation potentials and the reduction potentials based on this difference in donor groups which are attached to the centrally acceptor unit. And on the basis of this, by using these formulas, which is used to calculate the HOMO energy level and the LUMO energy level, these are the standard formulas which are available in the literature. We have calculated the HOMO and LUMO energy levels. You can see here the molecule 1 means it's an adduct, the acceptor, pyridopyrazine indole, having HOMO level 5.75 and LUMO is 3.31 and electrochemical band gap is 2.44. Using these formulas and using the oxidation and reduction potentials, we have calculated the HOMO and LUMO energy levels of these molecules, and is found in 5.60 to 5.62. Here, in case of fourth molecule, which is having the methoxy substitute donor group on the phenyl ring, have this list HOMO level 5.17, as well as the LUMO is 3.18. So LUMO level of this molecule 2 to 6 is between 3.7 to 3.24. And the electrochemical band gap calculated using this formula obtained the through 2.36 in case of molecule 2, 2.31, 1.99 in case of molecule 4 is the least one, having this electron donor methoxy substituent on the diphenylamine. In case of cyclic donors like carbazole, in case of fifth molecule 2.43 and sixth is having phenothiazine 2.35. So this HOMO and LUMO energy levels are well matches with the ambipolar charge transporting materials which are reported or commonly used in optoelectronic devices. And thus, on the basis of this, we can claim these molecules are ambipolar charge transporting materials. The HOMO level to have this ambipolar charge transporting properties in the material or molecule, the HOMO level, it should be between 4.8 to 5.6 electron volt, and the LUMO level must be between 3 to 4 electron volt. And you can see here the HOMO and LUMO energy levels which lies within that range, and thus may act as an ambipolar charge transporting materials in optoelectronic devices with good against this the band gap or the lower band gap. So this is the electrochemical properties of this molecule that confirm the ambipolar charge transporting characteristics in this molecule. Now about the TADF characteristics, we have estimated the TADF property in these molecules using theoretical calculations by using this Gaussian basis set. This is the figure you can see here, the ground state S0 and the frontier molecular orbitals, natural transition orbitals for the S1 and T1 state, S1 and T1. This is, you can see the HOMO and LUMO molecular orbital diagrams for S0, ground state, singlet excited state, and the triplet state. And this is the optimized structure of this molecule 2. The ground state optimized structure of molecule 2. And this is the delta EST. That is the energy difference between singlet S1 and T1 state. That is 0.14 electron. Now, if you see this table, this is the computed table for it shows here the theoretically calculated HOMO LUMO levels, theoretically or computationally calculated band gap, the S1 state, T1 state, and this is the difference in this S1 and T1, that is delta EST. So this is of prime importance over here. Geometrical parameters of molecules suggest that twist state molecular conformation of donor and acceptor segment. Now twisting pattern you can see over here. This is the optimized structure of this molecule to having diphenylamine donor on this acceptor. So this diphenyl again is what is twisted. This molecule you can see this is not a planar one. This is a highly twisted. and thus forms this propeller shaped geometry. To have this AI activity, aggregation and distribution, as well as the TADF characteristics in the molecule it should be non-planar, highly twisted. And here you can see the molecule 2 is a twisted, it's a non-plane. And twisting pattern in DA assembly of dyes leads to efficiently charge separated homo-LUMO orbitals, wave function distributions, which causes reduction in delta AST value. You can see over here again these molecular orbital diagrams of these two in S0 ground state, S1 and T1 state. Now these homo-LUMO orbitals are well separated. Now this homo is totally on this one of the donor, that is diphenylamine, and LUMO is totally on this acceptor moiety, pyridopyrazine, indole moiety. These are well separated. If the orbitals in HOMO and LUMO, these are separated on throughout the molecule, so in that case, we cannot get this TADF property. To get the TADF property of characteristic in the molecule, the HOMO and LUMO orbitals, wave function, distribution should be greater than, well separated. And this also in case of S1, you can see here the well separated HOMO and LUMO levels. And small delta ST values suggest an efficient TADF emitters characteristics of this molecule. You can go through this table. The delta ST values which are obtained in case of molecule 2 is 0.14. In case of adduct, this pyridopyrazine indole derivative is 0.21. And these are very less than this value. In case of 2 having diphenylamine is 0.14 delta ST value. In case of 3 having methoxy 0.13. In case of 4th is 0.13. In case of cyclic amines, now you can see in case of 5th molecule having carbazolamine as a donor 0.05, and very least in case of molecule 6 where the donor is phenothiazine, and that is very highly twisted molecule. Okay, and this delta ST value is very least as compared to this other derivatives and this adduct. It's in case of molecule 6, 0.01. So thus, in these molecules, the pyridopyrazine indole amines, we obtained is very less or very negligible or minimum against this delta EST values, and thus these molecules can act as a TADF emitters in further applications in optoelectronic devices. In this slide, you can see this comparable experimental and theoretical data. So this is the simulated absorption plot of 1 to 6 in gas phase, computationally obtained. Again, the transitions about 400 nanometer confirms here the ICT transition, that is intramolecular charge transfer, and thus DAB feature in this molecule or donor acceptor characteristics in this molecule. This plot you can see here, the graph of experimental absorption and theoretical absorption values, which are again the well matches. This plot you can see the electrochemical band gap versus optical band gap. This plot here is electrochemical band gap and theoretical band gap, and optical band gap and theoretical band gap. So whatever the experimental obtained data is there, it is well matches with this theoretically calculated one, and that gives the strong support to this experimental data. So thus in conclusion, it can be concluded that the intramolecular charge transport property of this characteristics is obtained by CN coupling of various amines with this pyridopyrazine indole unit in all the dyes. These dyes emit in blue to yellow region in solution state as well as in solid state. Emission characteristics in case of dyes 2, 5, and 6 sustain positive solar diffraction as suggested from various solent polarity function plots. The lesser extent of pi conjugation in die 2, 5, and 6 than 3 and 4 offers strong solid state emission by effective restricted intramolecular motion, hence undersigned or acquire the AIE phenomenon. The formation of emissive nanoparticles at high water fraction of THF water mixtures in case of die 2, 5, and 6, it was confirmed by DLS data. Anti-Stokes shift properties in case of die 3 and 4 recommend its various its application in biology or biofield bioimaging. The measured HOMO and LUMO energy levels, these are found comparable with the reported ambipolar materials. The electrochemical band gaps, optical band gap, these are in correlation with the theoretical values, which are calculated by this basis set. Then TDDFT calculations verify one, the presence of donor acceptor architecture, thus intramolecular charge transfer in this molecule. And second, the dependency of photophysical characteristics on variation in electronic structure and geometrical parameter at ground and eccentric state. The larger homolumo orbital charge separation and dominant charge transport excitation characteristics from donor to acceptor, leading to lower delta EST values that range from 0.01 to 0.14 electron. Hence, shows the possibility of TADF characteristics in this molecule. The delta EST value should be less than 0.3 electron volt, and we obtained very negligible in case of molecule 6 in 0.01. And thus, the experimental and theoretical results warrants the potential use of these molecules for their applications in these optoelectronic devices. And this work is published recently in Journal of Luminescence. If you want to have this more knowledge about this, more data, so you can refer this paper titled this. At last, I thank you all of you for your kind attention. Thanks.
Thank you very much, sir. This session has been quite an informative and encouraging one. Thank you for your valuable contribution.